for three. Rebound by Peyton Crispin. He's going to put it back. And he got it! The Lakers hit a three.
Welcome back again. Music Park, home of your SWOCC Lakers.
Can't get the shot to go. The Lakers win the ball game. Go! Lakers win! Lakers win in overtime. 108-106.
Do you like to work with metal, fire, electricity? Would you like to make money doing it? At Southwestern, we can help make your dream a reality. With our degree and certificate programs in welding, you'll be prepared for a career in the welding and fabrication industry in as little as a year. Check out our website and let Southwestern spark your career in welding today.
Southwestern Oregon Community College gave me the opportunity for a new career doing something I love. I'm Amber Yardley, and 3 years ago, I knew I needed to make a career change for myself and my family. With the support of staff, my academic advisor, and the instructors at SWOCC, I now have a dream job and the confidence to continue my education. Contact Southwestern Oregon Community College and start the journey to your new career today.
This is Southwestern's Dental Assisting Program. In just one short year, you could be a dental assistant. Sign up now for your one-year dental assisting certification.
Congratulations, you just got accepted into college. Now, how do you pay for it? Fortunately, there are several options out there to consider. Follow this simple step-by-step guide as you figure out how to pay for college. Step 1. Fill out your FAFSA? Free Application for Federal Student Aid, FAFSA. Your FAFSA will determine if you qualify for financial aid, including grants, some scholarships, work-study, and federal student loans. The good news is, most people qualify for some financial aid, which is why this is the most important step in figuring out how to pay for college. Step 2. Figure out how much you may need to borrow by weighing your college costs versus your contributions, including any grants or scholarships. Some easy arithmetic will make your math teachers proud. Let's say your college of choice costs $30,000 a year after factoring in tuition, housing, books, lab fees, and a laptop. Now, let's pretend that the money found in your family swear jar, your bowling scholarship, your federal grant, and the money you saved as a scuba instructor contributes $10,000 to your college fund. Voila! This is how much you will need to cover through other means. Many families consider student loans a reliable option. Step 3. There are two categories of student loans you can consider: federal and private. Federal loans are made by the government and private loans are made by private lenders. In some cases, families use both to cover the cost of college. Compare student loan options by looking at their interest rates, repayment options, and fees. Interest rates vary depending on the loan type. Federal loan rates are fixed, while private loan rates can be fixed or variable and are determined by your credit quality. Adding a co-signer, like mom and dad, may help lower your interest rate. Repayment options for federal and private loans are also different. Some providers require in-school payments, some don't. Take a look at these now and choose an option that makes sense for you. Watch out for fees. Fees can be charged upfront or in repayment, and they add to the total cost of the loan, so you end up paying more back. Step 4. Factor in other benefits when researching a loan. Some reduce your interest rate and some give you cash back. For example, Discover student loans have no fees and give you a cash reward for a 3.0 GPA or equivalent. Let's go through these steps one more time, just in case you needed a refresher. Step 1, fill out your FAFSA. Step 2, weigh your school cost versus your contributions. Maximize any free money like personal savings, grants, and scholarships before considering loans. Step 3, compare interest rates, repayment options, and fees. Step 4, take into account any benefits the loan provider may offer. Don't forget that you can continue to reduce the amount you need to borrow with scholarships. If you are an eligible current or college-bound student, you can enter to win a $2,500 Discover Student Loan Scholarship Award. Head over to collegecovered.com to learn more about paying for college and enter to win. No purchase or loan required.
So, and of course, everything that I'm talking about is a team effort. I couldn't do all this work on my own, that's for sure. And there's a bunch of people who have supported this. And it's nice because we bring together applied math and to write the equations for how seismic waves travel through the Earth. And then we put that in a computer program that has to run efficiently on a big computer, not just a laptop, but on a supercomputer, which has lots of laptops connected. We want our ground motions to be relevant for engineering applications. So we work closely with engineers, and we couldn't do this work without supercomputer centers that provide the resources of the computers that we run on. Okay, so I work at Lawrence Livermore Lab. Livermore lab was started it has its roots in the University of California, just like Los Alamos Lab is part of the Manhattan Project to build a nuclear bomb during World War II. It moved out from Berkeley to Livermore in 1952 and was started by E.O. Lawrence and other professors from Berkeley. And the idea was to be a sister lab to Los Alamos, which had created the nuclear bomb that ended World War II, and to provide alternate ideas. But it was sort of centered on nuclear weapons and national security. And one of the key things was, one of the key founding ideas of the lab was to have multidisciplinary team approach to solve complex problems. So it's very common for us to have, engineers and mathematicians and computer scientists and physicists working together. And computing has always been a big part of Livermore, and we benefit from the computing that's done for all the national security nuclear weapons work. We are able to now, we've spurred that off, and now we look at earthquakes and climate and chemical processes and all sorts of other, how stars form, etc. So these big computers sit in a big, giant building with rooms with, football field areas full of computers. And so we're, now the reason why there's seismology at Livermore is because nuclear weapons tests, underground nuclear tests, generate seismic waves, just like earthquakes, and they can be observed from far away. And that's most of what we know about foreign nuclear tests is through seismology. So that's why we have a seismology program, and that's I started doing other things 20-some years ago when I started at the lab. But now I work almost exclusively on seismic safety and earthquake shaking. Okay, so you might ask the question, why use computers to model earthquakes? Well, large damaging earthquakes, they occur on faults, so they're not everywhere, but they're usually isolated to faults that have been mapped. And fortunately, they're infrequent, or relatively infrequent. That's the large damaging earthquakes. But the consequences are very serious, and they impact, our well-being and our economies and our health and safety, et cetera. Now, seismometers are not everywhere. Those are the devices that record the shaking, and they're very sensitive, much more sensitive to the accelerometer we have in our phones now, but they are sensitive so they can measure very, very small vibrations. And, but we can't capture the shaking everywhere because we can't have seismometers everywhere. So that's a challenge, and computer modeling allows us to fill in those gaps, and especially close to faults, and that's where the shaking's most intense, as you'd expect. So consequently, we have very few recordings of large earthquakes at close distances where all the action and all the damage happens. So, and earthquake scientists and engineers work with the available data to build models that describe the ground motion shaking intensity and as a function of magnitude and distance and other things. And important facts to sort of keep track of, the ground motion intensity, or the strength of shaking, depends on various factors. First, the magnitude. Magnitude is a measure of the earthquake size, not the measure of the shaking. The shaking is something we experience, right? But the magnitude is a property of the earthquake that measures the physical size of the fault and how much it moved. Now, the closer you are to the fault, at low distances, you experience stronger shaking, just like any wave, just like the voice, any sound is louder if you're close to it. And same principle of waves. So distance is an important factor. The further you go away from the earthquake, the weaker the shaking generally. But thirdly and importantly are earthquake and local geologic details, particularly the type of soil you're sitting on. If you're on sedimentary soil, weak soils, dirt, sand, it tends to amplify the ground shaking. If you're on hard rock, you tend to have lower shaking than you would otherwise. And so in the absence of empirical data, without observations, we have limited observations, computer modeling provides us a way to forecast what earthquake shaking will be for a specific fault. And the Earth is a challenging thing about working in earth sciences is that geology is variable everywhere, right? You go in any direction, you're going to encounter different rock types, different geology. And that geologic structure impacts how seismic waves travel through the material. And so when we're looking to build, a critical facility or our house or, a school or something, a hospital somewhere, we want to know what is the site-specific ground motion for the specific geology and the orientation of faults for that particular region, which is probably not matched exactly anywhere else in the world. So computer modeling helps us to fill that in. Okay, so if we just zoom out and think about why we have earthquakes, right, we have plate tectonics as sort of the unifying theme or principle of what we experience on the surface with geology. The Earth is hot on the inside. That heat's trying to get out. The mantle circulates. It drags these tectonic plates at the surface. And sometimes there's cracks between those plates to take the plate tectonic boundaries. Like we have the Pacific plate. If we go out into the Pacific, we're on the Pacific plate. If we go inland into the center of Oregon, we're on the North American plate. And there's a plate boundary that separates that. And earthquakes and volcanoes tend to be concentrated on those tectonic plate boundaries. So zooming in here, looking at California and the West Coast, we've got the San Andreas Fault, a major strike-slip or side-to-side fault that cuts through most of California. And then offshore in Northern California, Oregon, or northernmost California, Oregon, and Washington, we have the Cascadia subduction zone where oceanic plate is going underneath the Pacific Northwest and can cause a different type of earthquake than what I'll talk about for California. And then if we zoom in closer on the Bay Area, so whereas in Central California and in north of the Bay Area, the San Andreas is really one main fault, and the plate boundary is mostly along that fault. In Southern California and in Los Angeles, there's a very complex network of faults, not unlike what we have in the Bay Area. And in the Bay Area, we have this picture where we have the San Andreas Fault going right underneath San Francisco, but then the Hayward Fault and some other faults that are sort of parallel to it. And the deformation associated with that plate boundary is distributed across these faults that cross the Bay Area. Now, seismologists look at the occurrence rate of earthquakes and the magnitude of those earthquakes, and they can characterize how often earthquakes happen on a fault and what is the maximum size, and that's put in together with models for what the shaking of those earthquakes would be to determine the seismic hazard. That is, what is the likelihood that the ground motion intensity or the shaking intensity exceeds a certain level over a certain interval of time. And that's been done in the Bay Area. Now remember, we had the 1906 rupture on the San Andreas Fault that ruptured quite a long area, about 300 miles, and that was a magnitude 7.9 earthquake. And then we had the Loma Prieta earthquake down in the Santa Cruz Mountains 30 years ago. Just recently had that anniversary. So there's been, those earthquakes reduce the likelihood. So the San Andreas isn't the top contributor to seismic hazard in the Bay Area. It's actually the Hayward Fault and its northern extension, the Rodgers Creek Fault that goes through Santa Rosa. So there's a 30, and then, the numbers that you get out of this seismic hazard analysis indicates that there's a 33% chance, for the whole Bay Area, there's a 72% chance, so better than 2/3 chance, of a magnitude 6.7 earthquake or greater before 2043. So before the mortgage, if you were to buy a house today, right, the mortgage would basically, be be complete, within that time frame. And that's anywhere in the Bay Area, but if you de-aggregate that hazard into specific faults, the Hayward contributes 33% of that hazard. So it's the most likely major, next major earthquake. Now, in 2014, I didn't know about the West Napa fault, but it ruptured with a magnitude 6 earthquake. And of course, there are lots of faults in the Bay Area, and there are many, they've been mapped, and many of them are capable of magnitude 6 and higher earthquakes. But this is looking at, the longer history and the possibility of large earthquakes up to, say, magnitude 7. So in about almost exactly 51 years ago now, the Hayward fault ruptured with, we didn't have precise seismometers to measure the intensity of shaking and estimate the magnitude, but it's estimated that there was a magnitude anywhere from 6.5 to 7.2 earthquake on the Hayward fault. It caused significant damage at the time, but fortunately there were only about 3,000 people living in the East Bay at the time, or on the eastern shore of the San Francisco Bay. But the shaking was intense and caused damage even in San Francisco, as seen in that photo there. This is sort of the before and after picture of the Alameda County Courthouse. So those reported experiences of shaking are compiled into make something called a shake map. And there's a scientist at the USGS went back and he, analyzed newspaper reports and, went through the history and precisely located where those reports were made, and each of the yellow diamonds or yellow symbols is a place where there was an experienced report. And those are all compiled together into a shake map, and the shake map with the red colors indicates the strongest shaking, and then orange is a little bit less, and yellow less than that, and then green and blue, etc. But on this scale here with that yellow, everyone on this map would feel this earthquake. I mean, this is a big earthquake. Even 100 miles away, you would probably feel this earthquake. And the black line indicates the surface rupture. So that basically says that, yeah, the earth here, this is on top of the earthquake. There's actually deformation at the surface that cracked the soil and indicated that there was motion. So this is what is possible and what happened 151 years ago. So now seismologists and earthquake geologists can dig down into the soils across the fault and and they build a trench here that crosses the fault. And then they can look at the soils and how they're disrupted. And they can also take little samples and do precise carbon dating and date those past events. And there's evidence of 12 earthquakes on the Hayward Fault. So this is 1868 here, and this is going back in time, almost 2,000 years. And there's evidence, there's air bars, of course, because of the dating, that that's imprecise, but it indicates that about every 150 years, there's a major earthquake on the Hayward Fault. So the only math to really, that I'll want you to think about tonight is, we've got evidence, very strong geologic evidence that every 150 years there's a major earthquake on the Hayward Fault. So the last one was in 1868, so here we are, 2018. So now we're entering kind of the overtime of when you would expect, or you're past the median prediction of when another earthquake should happen. So, and of course, things have changed in the Bay Area since 1868 tremendously, right? Here's the population density here, where the red values now in this map are indicating the densely populated areas, and you've got Oakland and Berkeley, Fremont, Hayward, of course. San Francisco is very densely populated. If you look at the counties of Alameda County, Contra Costa County, and northern Santa Clara County, there could be 2 to 4 million people that are strongly impacted by this earthquake, depending on where it happens. Is it further south, or is it further north, or does it rupture the whole thing with an even bigger earthquake? All right, so because it was the anniversary recently of the Loma Prieta earthquake in 1989, it's interesting to compare the shake map. So this is a shake map from 1868 on the left that shows the interpretation of felt reports. And on the right is 30-year-old science, but the interpretation of what the shaking intensity was from actual measurements. And of course now we have more instruments that are probably more precise, and they have modern technology and can communicate in real time and stuff. And of course Sarah will talk about that in January. But you can see there are very strong similarities between the pattern in that the red values are close to where the fault happened. And I didn't indicate it here, but the Loma Prieta rupture was in this part of the Santa Cruz Mountains, whereas the Hayward fault, ruptured here, and you can see those red values. Those red values, they correspond to shaking that's intense enough to cause damage to buildings. So the peak ground velocity can be 1 meter per second. So that means the ground goes from here to here and back in that time. And it also corresponds to shaking intensity or acceleration of greater than the acceleration of gravity. So the force that presses this onto my hand, could be applied in horizontal directions. And that's what causes damage to buildings. If you take the base of the building and you move it over here very quickly, the top of the building can't respond, so then the building starts shaking. And it's interesting to see the construction of a new building and see on the inside, a modern steel frame building or these reinforced concrete buildings, that are built to modern practices, should be able to withstand that level of shaking. And I believe here you're probably expecting to see something like that if there's a major Cascadia earthquake. All right. So we learned a lot, though, from the Loma Prieta earthquake. And it illustrates some really important points, that the shaking is intense near the center, and this is sort of in the Loma Prieta epicenter zone, where there's really strong deformations, including vertical motions that went right through these people's front yard. Downtown Santa Cruz was really devastated. They had to close down the Pacific Garden Mall for quite a while. And we see that, of course, the shaking intensity is intense close to the fault. But then one thing that really came out is the effect of soils really matter. And 75 miles away in Oakland, the cypress structure of the 880 freeway collapsed. And the section that collapsed corresponded very closely with the transition from hard soils to a segment of soft soil. And the damage and the collapse occurred on the soft soil part, but the parts on hard soil were not as damaged. And there were also effects of different waves coming in at the same time. So the large-scale structure of the crust, it turns out there was a wave that was coming along the surface and another one that came underneath it. And they hit, you can see this area of very intense shaking where the cypress structure is, but also in the marina, those were about the same distance away, and that simultaneous arriving of energy happened at those sites and contributed to the damage. So those kinds of effects occur when there are these types of conditions that are specific to the crustal and a geologic structure. Okay, well, if we take, let's see, so the week of the Loma Prieta anniversary, on August 14th, there was an earthquake in Pleasant Hill near Walnut Creek, so maybe about, maybe 15 miles east of Oakland. And it was a magnitude 4.5. I wasn't home at the time, but I got a call right away from my wife who felt it. And I was then busy that night to then go and get the data and make these measurements. And this is the measurement of the peak ground velocity as a function of distance. And you can see it's highest near the fault, and it falls off just like we expect. And then there's an average, what you would expect for that model is the black line, and then plus and minus a variation, the dashed lines. So this agrees pretty well with our models, but there are always deviations. And one of the important parts aspects of earthquake ground motion is the variability. And the ground motions are variable. And we still, despite all the work we've done to try to understand ground shaking, we can't tell or untangle all the different components of that uncertainty. There's uncertainty due to how quickly the Earth happens in time, or how compact it is in space, or how spread out it is in space, how waves travel through complicated geology, how they arrive at a site. And we can have two sites that are the same distance away from the earthquake in the same direction, more or less, but they have very different ground motions. And that's reflected by the variability. And you can see in terms of the intensity levels, this is, and we have this quantitative or qualitative scale called the modified Mercalli intensity scale, which translates our felt experience of the earthquake, like did chimneys knock down, were things knocked off the wall, did you not feel it? All that qualitative stuff can be put into that Mercalli intensity. But you can see we have quite a lot of variability in those intensities. All right, so if we go around the world and we take all the earthquake data and compile it together, and we look at where each dot represents a recording or a seismogram of an earthquake of a certain magnitude, from small to big, plotted on the y-axis here, and how far away was it from that earthquake, from 100 meters to 1,000 kilometers, this is what we get. And we have a lot of measurements around between 10 and 100 kilometers. But less than 10 kilometers, we don't have that many. And what's especially frustrating is for those large earthquakes, we don't have many recordings. And so despite our efforts to go, and deploy seismic stations everywhere, you still have to wait for these earthquakes to happen. And that's a big challenge for earthquake science. Earthquake repeat times can be 100, like the Hayward fault, 150 years. For Cascadia, it could be 300 years or more. So we've only been recording seismic data for a couple of decades by comparison, very short by comparison to the return time of earthquakes. So, but nonetheless, we have to make models from these limited data, and we have to mix data from all over the world. So our estimates of shaking in California are based on earthquakes in Italy and Japan and Southern California and Turkey and China. And we have to then try to tease out some systematic effects there. All right, so computer modeling is an attractive alternative to then relying on the limited data. So if we understand how earthquakes happen, and we make a model of how the earthquake happens, and this figure shows kind of how much the earthquake slips, how much one side moves relative to the other on the surface of the earthquake. And if we have a model of the geology and the physical properties, the density and the elastic properties and the wave speeds, we can put it into a computer program that does the math to solve how those waves propagate in time. And in order to do that on a scale that is able to produce results that are relevant to, say, how buildings respond, to capture the waves that are short enough that correspond to the sizes of buildings, say. We need to do it on supercomputers. We can't do it on laptops. We just, they're not that powerful. We need billions of grid points to discretize the area, and that's what I do. So here is a model that the USGS has produced of the geology of the Bay Area, and they've assigned properties to each of these geologies. And now I've taken a map of the Bay Area and turned it on its side, so north is kind of going up and to the left. And this is one particular property of the seismic wave speed. And the Hayward fault cuts through kind of the center of this. So I'm looking at the white box. So that's a box. I have a, sort of that box represents a volume of the Earth that I'm going to model. And we put in the Hayward Fault, which goes right through the middle of that. And you can see there's quite a lot of variation in the geology and in the material properties due to just different geologic structures. Particularly across the Hayward Fault, the wave speeds are very different. Now, this is the earthquake model, so this shows how much the earthquake slipped in centimeters. So that's 1 meter, 2 meters, 3 meters. So at depth, for a magnitude 7 earthquake, the rock can move on two sides of the fault, can move so from here, across the stage at depth. Okay, so imagine how strong that material is, and it's able to support kilometers, right? This is down a few 10 to 15 kilometers. It's supporting the weight of all that. And there's so much energy and so much strain energy that's been built up from plate tectonics and mantle convection. It exceeds the breaking point of the rock. That rock takes off and it moves across the stage. So imagine that's a lot of energy, right? That's a lot of mass and a lot of force to do that. And that energy is released as seismic waves, which then ripple through the Earth. So we seismologists have looked at earthquakes of this size and characterized how the slip occurs, and then we have a mathematical model to generate a realization of one possibility for this magnitude 7 earthquake. And as these calculations get easier, we can sample many of them, right? That's the idea, because it's hard to know in advance where these slip patches are going to occur. And that's something we study, and they tend to be places that are locked, places that don't give up motion, that aren't relieved during small earthquakes, but they tend to be locked. So once they break, they have a tremendous amount of strain energy released into seismic waves. So potential energy is converted into kinetic energy. So the hypocenter is the place where the earthquake starts. It tends to start in a place where there's very little slip. And it's believed that a magnitude 7 earthquake is just a magnitude 1 earthquake that didn't stop. It's a chain reaction. A magnitude 1 cascades into a magnitude 2, into a 3, into a 4, into a 5. And an earthquake, a magnitude 3 earthquake, is one that just stopped. It couldn't maintain that chain reaction. There are certain patches, these slip patches, are where there's locked parts of the fault that when they rupture or when they break, they release a lot of energy, and they have a lot of slip, which then generates a lot of that energy. All right, then we take the Earth and we break it up into a grid of cells, and we then characterize the properties there, and then we step through time and we adjust the stresses and the strains inside the Earth, and that's how the waves travel. So we just basically look at snapshots at regular intervals, and we update where the wave is going. So the wave starts close to the hypocenter and moves out and out and out and out and stepping through time. And for some reason these animations aren't working, but these would show little kind of cartoonish views of how the shaking and the waves travel. All right, well for this, so then the question though is, it's a computer model, and we can give you whatever result you want in a sense, right, by just adjusting the inputs. And a key thing is using physically constrained inputs. But we do want to test our models with independent data. So this earthquake occurred in Pleasant Hill a couple weeks ago. It was felt by all these people in the Bay Area. Each one of those squares, at least one person went to the USGS website, did you feel it, and entered in what they felt. And then we've got these seismometers. Each triangle represents a seismometer that recorded the event on the night of the earthquake, too, which was 10:30 p.m. So there are probably about 200 stations there. So we can go download that data, and then I can run the calculation. And it's instead of it being a big, extended magnitude 7 earthquake, it's essentially a point source as a magnitude 4.5 earthquake. And I've got the 3D geology model. and I run that calculation. And here's a map that shows the red circle shows the earthquake location, and then there are two sites, BDM and BRK. One's out in Mount Diablo, and here are the three components: the shaking in the direction across from the direction of propagation, in the direction, and then the vertical, T's, R, and Z. And the blue shows the data, and the red shows the synthetic seismogram calculated with the full 3D geology. And then we have ways to measure this in the frequency domain and such. But suffice to say, and then here's the station down to Berkeley. Again, the red is the calculation, the blue is the data. And we get a good match here that gives us encouraging sense that we validated that we put the right physical inputs into the model, we get out data that's like the measurements and gives us confidence. And then for a comparison here, here's another earthquake that occurred near San Jose that's recorded way up here. And this is a simple pancake layer model, a one-dimensional model. So mostly the Earth is stratified, right? Once you have all that rock on top of you, that weight tends to homogenize things. And Earth structure generally, the wave speeds and density increase with depth. But geology breaks that because some rocks of different material types, they have a different history, they've been heated or cooled in a different way, have different properties. And so the Earth structure is inherently three-dimensional. It varies in each direction, up, down, side to side, etc. So a simple one-dimensional model is shown in red here. It can't produce the long duration of shaking. There's not enough scattering of the waves or shaking of the waves. But the three-dimensional model gives a very good character, and it fits these amplitudes much better. So that's an example of, we can reject the 1D model, and then the 3D model is good. Now the question is, well, how do we improve that model? How do we, make it, how do we identify places where it's not good, and how do we update that model? And that's a challenging problem. Okay, so we then put for the Bay Area, this is again the Bay Area turned on its side. So here's San Francisco's here, Oakland's here. Here's the Hayward Fault. We took the Bay Area and rotated on its side. And this is a snapshot of the shaking intensity in that same color-coded scale where the red corresponds to very strong shaking that would cause damage to buildings. And, and then it drops down into the orange and yellow and green, etc. So if we go to the next slide, and then in Dallas, this is the animation. So this is going to show an animation of the waves traveling out from the hypocenter, and you're going to see a lot of complexity in the wave field. So that's sort of an end result picture of a shake map that is derived from the calculation. So at 0 time, the time is up there, moving up is 4 seconds. So now the shaking intensity starts to get into the yellow. Now it's getting into the reds. There's a lot of structure differences on either side of the fault. And then the waves start to encounter the sedimentary structures in the San Pablo Bay and down here in the Evergreen Basin, and there's a San Leandro Basin. Out here in the Dublin, Livermore, Pleasanton Valley, there's a lot of surface waves and shaking that corresponds to the sedimentary basins. And long after the event has stopped, these basins continue to shake because waves get trapped in them just like waves in a bathtub, and they bounce around and they take a long time to die down here, even after a minute or so. And there's still quite strong shaking, right? You're seeing values that would make us jump under our table or our desk if we were at work. All right, and then after 60 seconds, so the earthquake takes about 25 to 30 seconds to happen, but the waves take a full minute to travel out, and we calculate for a minute and a half. But at this point, the shaking is down, but almost everybody, anybody in that box would feel the earthquake. The shaking is that intense. All right, let's go back to the presentation. There we go. Okay, so from the calculation now, these are the peak ground acceleration and the peak ground velocity as a function of distance from 100 meters to 60 kilometers. And you see the measurements have a lot of variability, but they kind of are bracket what we expect from the prediction. So this model, the median model, the solid black line, is derived from worldwide measurements of, say, magnitude 7 earthquakes in Taiwan and China and Italy and Southern California, et cetera. They're all put into a model, and their uncertainty is indicated by the dashed lines, and we get good agreement there. So this gives us confidence that we're producing simulated ground motions that are consistent with what's measured. One of the points I haven't emphasized, but it's important to say, is that we're able to go to higher and higher frequencies to use smaller and smaller spatial discretization, which requires bigger and bigger computers to be able to do these calculations. So a few years ago, this calculation wasn't possible, and then it's become possible a few years ago, and now it's routine in the time that we've been doing this, because and I'll talk about this a little bit later, but in the past we weren't able to model the detail at the level that we can now. And let's see. So here, so if we go back to that shake map of the 1868 earthquake, there were intensities experienced, Mercalli intensities of 7, 8, 9, and our simulations are producing intensities that are consistent with what was experienced in 1868. So we're not trying to model exactly what happened in 1868. That's a really hard problem, and we don't have the data to constrain it. But this is showing that, and I've done several of these, and I can, convince you, hopefully, that we get consistent results at that same level. All right, so now, so what? We can calculate ground motions. Well, we want to work with engineers to help them design safer structures. And there are sort of two pathways there. So we can run a calculation and generate a ground motion. And one pathway is to apply these motions to the base of tall steel frame buildings. And our colleagues at the University of Nevada, Reno, and Lawrence Berkeley Lab are doing that to be able to tell what is the likelihood of damage to, say, canonical, 3, 9, 20-story buildings. And they can make maps of what that damage would look like. Another area of research is when you want to look at, say, a critical infrastructure like a nuclear power plant. Sometimes we have to build our buildings next to faults where we know the ground motion can be very strong. So we want to choose to build those strong enough to withstand the expected shaking. Well, we can give you the expected shaking or several realizations of that, and then one could calculate, and for this we have to output many points, the shaking at many points, and they're applied to this model that includes the soil and, say, a nuclear power plant or a bridge or a tunnel or something like that. All right, so on this point of resolution, there's this, the smallest size of the calculation I showed is on the order of 10 meters, right? And that helps us resolve frequencies of up to, say, 5 hertz. So now this is a spectrum sort of showing a variety of engineered systems, from pipelines and long-span bridges, which are sensitive to the longest period motions or the very slowly varying waves. And as you go from those very large structures, which are sensitive to low frequency shaking, to smaller structures like energy components and transformers and things, or nuclear power plants, which are designed to be very heavy and very stiff, so they're sensitive to very rapidly vibrating waves. They're sensitive to higher frequencies. But The challenge is in order for us to resolve those frequencies, we need sort of 8 points for a wavelength. So if you think about one cycle of a sine wave, we need to have 8 points to sample that. So if we want to go to really high frequency, we have to have very fine spatial granularity. You know, in the past, 20 meters was about all we could do, and now we can do 10, and now we can do 5. And it turns out, though, the effort to go to double the frequency means we have to have twice as many points in the, you know, in the x direction, and the y direction, and the z direction. So there's 8 times more, 2 times 2 times 2 more points, and we need 2 time steps, twice as many time steps. So the effort is 16 times harder. So the curve to increase the frequency is very steep. It goes as frequency to the 4th power, or a factor of 16. So to go from 1 hertz to 2 hertz, it's 16 times harder. To go from 2 to 4 is another 16, so 1 to 4 is 256, etc. So it's a really steep curve. But as computers get more and more powerful, we can move up that curve. And this shows sort of as a function of the resolved frequency on the x-axis and the number of grid points, or the total computer memory needed to store that. And each point is a calculation we've done. And this is one we did in 2012, and this was 2014, and these are sort of the 2017, 2018 runs we did. And now we're up here where we're running, you know, on hundreds of billions of grid points, and running on some of the most powerful computers in the world that are at the Department of Energy labs. So, you know, let's do a few comments to end here. Moore's law is the observation, right, done by Gordon Moore in the 60s, that the number of transistors in a dense integrated circuit doubles about every 2 years, right? We all know that computer, you know, devices just get smarter and smarter, you know, and the ability to squeeze you know, circuitry into smaller and smaller packages has made them faster and faster. So if we just look at, you know, the top, let's see, this orange dots are the gigaflops. That is a measure of computer power, the number of floating point operations that can be done in a second as a function of time going back, you know, a couple of decades. And if we look at, you know, the fastest computers, are a faster computer in the top of that 500 list of top 500 most powerful computers is in the orange, but the 500th is shown in the yellow dots, and then the doubling, if we were just to double that every year, we'd get the blue line. So we're beating Moore's law. Supercomputers are getting more and more powerful. And that's enabling us to be able to do these calculations a lot easier. So computers just keep getting more and more powerful. They're enabling, you know, radical changes in how science and engineering approaches these challenges. You know, we can now generate ground motions specific to a site, and it can be used in engineering applications to try to design, you know, a building to be safe at a certain level, you know, on the trade-off between design and your aversion to risk. And we anticipate that, you know, of course, technology companies, they anticipate that this growth is going to happen. And I would argue that, you know, we should be expecting that our computer modeling is going to get more and more powerful and start to incorporate this in, you know, performance-based design of engineering structures. All right, so in summary, the Hayward fault in Northern California is capable of large damaging earthquakes. You know, and now we have the likelihood of strong shaking in a densely populated area of the East Bay. And we're close to the recurrence interval of the last major, say, magnitude 7 earthquake. Computer modeling of moderate earthquakes reproduces good agreement with the observed motions, and this gives us confidence or validation that we've got good tools to be able to model ground shaking. Our computer simulations of a magnitude 7 earthquake generates ground motions that are consistent with the models that are based on empirical data. and that these simulated motions are useful for engineering applications to design buildings and bridges or understand how they should be retrofit or something like that. Also for earthquake early warning, which I didn't talk about, but save it as a question for Sarah and when she's here in January. And lastly, right, if an earthquake happens, be prepared before it happens. In the Bay Area, as I was talking about this at the Loma Prieta anniversary, we're having power outages with PG&E, so your earthquake hit becomes your power outage. Of course, you have storms here and other consequences that would want you for which you'd want to be prepared. So have that kit and have that communication plan for how you're going to get in touch with your loved ones wherever they might be scattered across the area that you live. And then when the shaking starts to happen, drop, cover, and hold on and wait for the shaking to end. And expect aftershocks too. A big earthquake, if you have a Cascadia magnitude 7, those 6s are going to be, they're going to be a lot of magnitude 7s and 6s as aftershocks. So that could be damaging as well after, as you're recovering from the first one. And and then this work, I just want to one more time acknowledge that my colleagues and funding agencies for this, and for IRIS and SSA for supporting this trip, and thank you very much.
Thanks, Artie. We've got time for a couple questions. If you have a question, if you raise your hand, I'll get you a microphone. If you hadn't signed those handy-dandy forms outside, if you would take a second on your way out as well.
I'm just curious, so when the large building or the size of the building, resonance determines the applied, how much force is going to be applied to that structure from the quake, whether those waves are large or small in amplitude and how frequent, right?
Yeah,
so,
it's really, so there's a rule of thumb, like a 10-story building is resonant to 1 hertz or 1 second waves.
Okay.
And then in a 1-story building, like our houses, are sensitive to 10 hertz or 10 cycles per second.
Okay.
So, now fortunately that high frequency energy dissipates as you move away from the fault. But you experience it when you're close to the fault. So for me living in Oakland, I worry about that because I live in a 1-story house. But for Cascadia, that earthquake is going to be offshore, so we're not going to experience too much 10 hertz energy here. But those 10-second waves are going to come in really strongly. And the bridge that I came across to get here today, is a large structure that's sensitive, or tall buildings are sensitive. And tall buildings in downtown Portland and Seattle, that's a concern for, say, a Cascadia type earthquake.
What's the most difficult or most sensitive? Like you said, 5 or 10-story buildings?
Well, it depends. So it depends on the hazard is specific to each location. So so here I don't think you need to worry too much about the high frequencies unless there are faults right under North Bend and Coos Bay, but like there are in the Bay Area as I described. So it's that's one important takeaway, is that the seismic hazard is highly specific to a location given the proximity of earthquake faults and the nature of earthquakes on those faults. I hope I answered your question.
I thought I heard you say cell phones, accelerometer, beginning of the lecture. Is there any kind of a connection or app or anything tying them in?
As a matter of fact, there are. Yeah. So the cell phone knows when you do this. there's an accelerometer to tell it that, turn it on, so, because it's close to your, you just moved it up, and it knows where gravity is pointing at every instance. So people at University of California, Berkeley, and others have tried to harness the accelerometers and to record ground shaking. Now, they're not very precise compared to the instruments that maybe cost a couple $1,000s that you would put out to record, very, precisely record weak shaking. But there's a MEMS technology that goes into these accelerometers that people are trying to use to densify networks, and that would be incredibly helpful.
Hi. Are you recording the earthquakes that are going on out in the ocean?
Yeah. So seismometers just record the shaking, regardless of where the waves come from. So the same seismometers that record, local earthquakes are recording big earthquakes in Japan or nuclear explosions somewhere on the other side of the world, or the hum of large offshore storms, particularly in the winter time. So all of that, and that challenge we have as seismologists is trying to unravel all of that, because the signal for one person is the noise for another. But seismometers record the shaking, that's experienced, and they're very precise, very, a thousandth of a micron, of motion can be detected. So they're super sensitive. Not these ones, but the instrument observatory qualities. And by having lots of observations at different locations, we can back project where those earthquakes are happening, including offshore.
Do you have any actual underwater seismometers?
Yeah, there are so-called ocean bottom seismometers. Getting them out there is expensive because it can be, $100,000 a day to have a ship to go deploy them, and there's a lot of risk involved too because they don't always come back. But folks at Corvallis, at OSU, there's an ocean bottom program there, and up and down Cascadia, there have been deployments of ocean bottom seismometers. And that really helps because by surrounding, the earthquakes that are happening offshore, particularly say in Cascadia, they've helped a lot to try to, because by only having seismometers on land, we're only seeing, one side of the events. In the future, there are ocean bottom cables, and there are ideas to try to have more permanent ocean bottom seismometers, but it's very challenging.
Thank you for the talk. I had a question on the amount of energy released that you talked about. The rock, when a rock breaks, there's a great deal of energy released. The rocks that are a certain depth are all solid, but when we get down to deep earthquakes, they're plastic rocks, basically, is my understanding. And do you factor this into the calculations, and how does the plastic earthquake work?
Yeah, so in California, we tend to have earthquakes, from the surface, not quite the surface, but they tend to be between, say, 3 and 15 kilometers depth. And after 15 kilometers, then you're starting to, the rock actually, so the rock, the temperature in the earth increases with depth. And everything's compact. You have radioactive elements that are just inherent, like, that's why we have radon, right? And there's uranium that's decaying, and that generates heat, and that heat is trapped in the crust. And so that, the temperature increases with depth. But at a certain point, the rocks start to melt, and they can no longer be solid. So that's a very important distinction, is that the earthquakes occur in the solid rock. Cascadia subduction has some solid rock that's going much deeper, hundreds of kilometers, than it is in California. At those depths in California, the rocks cannot withstand. They're not solid. They're plastic. So that is an important distinction. So below a certain depth, the rock becomes, plastic, and if you push it, it deforms, and it doesn't hold that strain energy that is later broken and we experience as an earthquake. So that's, and we use that information to constrain the models of the shaking. That goes, so that yes, indeed, that does go in.
Can seismometers kind of tell what type of fault caused the earthquake? Do they give off like different types of, vibrations, or do you just base it off the location?
Well, so it's a good question. So part of what we do as seismologists is, if you're just looking at a single seismometer, you've got 3 lines moving. You've got the up-down, the north-south, and the east-west motion. And, you'd see blips, those, there's nothing, it's noise, and then all of a sudden something comes in. And it's hard with only one seismometer, and it's difficult, if not impossible, to try to say something about the event from only that one blip, unless you've seen it before. So it's really by having lots of seismometers distributed around and correlating that data in space and time that we can locate earthquakes. But then we can do more. Once we've located the earthquake, and all of this happens now automatically. So, my wife called me. I was in Reno, Nevada, and she called me at 10:20 or 10:23 or something and said, we just had an earthquake. And I looked at the USGS website and I said, there was a magnitude 2 earthquake there, but you wouldn't have felt a magnitude 2. It took them, maybe less than 2 minutes to do all of that automatically, to take all the seismic data around there, identify on a single channel that there's a blip, see it on a whole network of stations, then correlate that data in time, locate the earthquake, and determine when it and where it happened, the 4, X, Y, Z, and time components that correspond to the location and origin time, and then post it on the website. So sure enough, we're on the phone, and I'm like, I'm hitting refresh, right? And there it is, a 4.5 earthquake in Pleasant Hill. That used to take, of course, in the old days, 100 years ago, you would write a letter, dear colleague, did you record, could you send us a copy of your seismogram on, in Göttingen, Germany for an earthquake in Japan in 1920. So technology, has helped us tremendously in seismology. And now from that laptop in my backpack, I could, in a hotel room in Reno, I could collect all that data and run a program. Well, first, to get all that data, which comes in a format that is, it's a computer format. It doesn't, I have to then convert it into the actual units of ground shaking. So it comes in digital counts, and it needs to be converted into, say, velocity in meters per second, and then make measurements on it and make those plots. But that can all be done within 10 minutes, and it could be automated to go even faster. So all of these processes have gotten a lot easier, and it's really the context of having lots of individual seismometers forming a network that operates together, and then trying to analyze that data together. We can then tell, did it slip this way or this way? And we can get into those precise details, but only by looking at a network, not from a single station.
So I'm sure that Dr. Rodgers would be glad to answer some additional questions out in the lobby if anybody has them. But I'd like to take just a second to, again, express appreciation not only to Dr. Rodgers for putting his time in his schedule, but also to Iris SSA for supporting the distinguished speaker series that brings folks down here, and also to all of you. Thanks to our IT folks for making it happen in the live stream world as well. And again, hope to see you, I can't believe I'm saying 2020, but at the 15th annual Cascadia anniversary talk, end of January 2020 on the 24th. And again, if you're looking for a gift, we've got a few signed copies, the big ones. It actually isn't just about earthquakes, it's about community and resilience. So thank you again, Artie, I appreciate your coming down.
Thank you.
And to all of you.